Thank you very much, and greetings to everyone. I see Professor Seman Juntak sitting in the front row. Very nice to see you. We stopped at this just after the proof of the n-dimensional unit cube having lower inductive dimension equal to n. And by the monotonicity, I have to be here, but you can work. Yeah, maybe later, 1 hour later. Yeah. Yes. She once took vacuum the carpet, but she can't do it. N-dimensional unit cube, which is the n-fold Cartesian product of the closed unit interval. We have proved using Brouwer's fixed point theorem that it has lower inductive dimension n. And this dimension is monotonous. Therefore, the lower inductive dimension of Rn is at least n. And you can easily show that it is at most n as well. We have proved that it is at most n earlier. So we disprove that this is what is the subspace theorem. N-dimensional Euclidean space has lower inductive dimension n. And this dimension is topologically invariant. Now we are the definition of the lowercase int uses open sets and the neighborhood of a point. And it usually utilizes something called separator or two closed sets. Now that, so if we replace the point and if we replace point by closed set, then we are going to separate two closed sets by open sets, which means we are in that very strong separability axiom, which defines usually normal topological spaces. For any two disjoint closed sets, there exists, each of them has an open set containing it, so that the open sets themselves are disjoint. So now we assume that X is a separable metric space with the inductive dimension n, still lower. We can quickly finish this batch of slides because yesterday it was just about finished. Let U be any open set of X and F is a closed set contained in U. Then there exists an open set V between the F and U, between the closed set with which U contains, such that the boundary of this intermediate open set has a lower inductive dimension, at most n-1. This motivates another inductive dimension, the concept of another inductive dimension, which is called uppercase. These are both done by Poincaré, but the systematic treatment appeared in Menger and Urisong. So this is the definition of upper inductive dimension. It has three clauses: initial clause, inductive clause, and completion clause. So we are now looking at normal spaces, which normal spaces mean that any two disjoint closed sets, each has an open set containing it, so that the open sets are disjoint. Initial clause states that negative dimension of -1 is attained exactly by, this is an agreement. This is not a statement that is to be proved. We agree that dimension is -1 if and only if the space is empty, just like in the lowercase. And the inductive clause is similarly stated as in the lowercase, but now we have closed set instead. So this is a closed set subset of the space, and that is an open set containing it. Originally, it was a point, an open set into which the point is a member, and using this boundary, having upper inductive dimension at most in -1, to define, to deduce that the space still has upper inductive dimension at most n. And this is true for n and false for n-1. This means this is a completion clause somewhat. We stop somewhere and then we get the exact number. And very similar. And then, of course, this is again ambiguous, this symbol, because we are encountering dimensions which are integers, at least as big as -1. And if for none of these integers, none of the finite integers, this is true, then we ambiguously say that the space has dimension infinity. This is undefined, this symbol. So this is the equivalent statement of the second clause, just like in the case of lower. And then immediately after that, we can easily prove that these two dimensions are equal always. So after doing this theorem, it doesn't seem to be necessary to define two of them, and one for any topological spaces and the other one for normals. So now these are equal for separable metrics. Separable metric spaces are normal. From the definition, because every singleton set is a closed set. So from the definition that of both of these, that the lower one is at most the upper one. Then you need to prove that the upper one is also at most the lower one, and that can be proved easily by induction. So when the lower one is -1, then the upper one cannot be greater than -1. So because the lower one is -1, if and only if the space is empty, which means upper one is also -1. So it cannot be greater than -1. And inductively assume that this is true for every separable metric space of a lower dimension smaller than n, and then you deduce that it is when the lower dimension of the separable metric space X is n, then you deduce that the upper one is at most n as well. So we have this inequality in the other direction. Two inequalities conjuncted shows that the two dimensions are equal. Now we are going to define the most important concept of going to understand the definition of the most important concept of the dimension for topological spaces. It is Lebesgue's covering dimension. And this is the one which is being used for topological spaces. This is also an integer dimension. Let's see here cover of a space X. We didn't say C is open cover or closed cover. It doesn't matter. It's just a collection of sets whose union contains the whole space. And then we call another cover D a refinement if every member of D is contained in some member of C. So the set members of this, the second cover is sort of smaller than the first cover. This is what we call refinement. So this is the Lebesgue dimension, very important Lebesgue dimension of topological spaces, covering dimension. And this is for normal spaces. We're not talking about norm spaces, normal. Metrizable spaces are normal. The weight dimension is defined to be the smallest integer n, such that for any finite cover of the space, there exists a refinement of the cover so that every point of the space is in at most n plus 1 of the members of the defined cover. Defined is also a finite cover. Now, if you remember from your topology that in the definition of a compact set is that if you take any open cover, then there must be a finite subcover. Then the set is called compact. Here we are, Lebesgue is taking, in the start, taking a finite open cover. We are not concerned about whether space is compact or not. In the start, we're taking a finite open cover. Finite open cover exists because X itself, the whole space is open by definition. Therefore, there is a cover which has only one open set that covers X. So finite open cover exists. So Lebesgue is taking a finite open cover and then he's claiming that there must be a refinement. If you happen to take the whole space as a cover consisting of only one open set, then every point of the space is in exactly one member of this cover, and you cannot really have, for any space, you cannot really have any other number than one. But why, the main thing about the key point about the definition is that there exists a refinement, which is finite open, such that every point is in at most n plus 1 open sets. This is a very topological definition of dimension. I expect usually a very crucial question here, because a student should really, if she is awake, should really now notice that starting from the Lebesgue, this definition here has nothing to do with the space being normal. But why, in the major premise, we assume that the space is normal? This is a crucial question, and if you haven't asked, I'm not going to, I don't know the answer. Not now, but I don't want to go into the answer. You should really ask this question and answer it yourself. So now, again, we go to the simplest possible non-Euclidean example of unit circle, and we prove that its dimension is at most 1. And of course, it can be easily proved that it's at least 1. It's at most 1 because if you have any finite open cover of S1, there exists a finite refinement. Whatever open, even if you take the whole space, S1 as the circle as the only one open set in your finite cover, then you can still find a finite open cover so that every point is in at most 2 of the open set. For example, if you have open arcs overlapping, three open arcs or 2 open arcs overlapping, they intersect on both ends, then this is a finite refinement, open refinement, so that every point is in at most 2 of the members of the cover. This proves that S1 has dimension. Now we can just call it dimension because this is the property. Dimension at most 1. Disk, you can easily prove that its dimension is at most 2. Closed disk, which is the interior of any circle union the circle perimeter as well, which is the boundary. This has an open cover. You should really be carefully doing this question, that if you cannot have a refinement of any finite open cover so that every point is in at most 2 of the members. But you can have a refinement of any finite open cover so that every point is in at most 3. So its dimension is at most 2, as you expect. Mesh is a topological space which looks like graph, because everybody in this room understand what a graph is. And it's mostly graph theory. So if you, but you cannot really, without some condition, you cannot really see a graph being a mesh, because for a graph, there are two types of objects, vertices and edges. But we are regarding the vertices as points as well, and interiors of edges as every point on the edge as points as well. That is called a mesh. So any mesh with finite number of branch points. So every degree is finite, which is essentially a locally finite graph. Even if the graph is infinite, but every vertex has finite degree, we call it locally finite graph is a mesh. If you regard vertices as points and every point on the edges, each edge as points as well, then this has dimension 1. Because there always exists an open finite open refinement of any given finite open cover, such that every point is in at most 2 of the open set. So theoretically speaking, every graph, if you agree that make that agreement, has dimension 1. And these are actually correctly called in topology as one-dimensional complexes. A knot is a continuous image of a circle. That's like a piano's definition of a piano continua. If you have a circle and if you have any topological space, particularly R3, three-dimensional Euclidean space, and then you have a continuous image of a circle, then it is called a knot. Of course, the continuous mapping can be straight realized in three-dimensional space as transformation. And this is because these are all homomorphic to, it's a two-way bijective continuous mapping whose inverse is also continuous. These are homomorphisms. So Lebesgue dimension, where you can easily prove that it's topological invariant. Therefore, every knot has dimension 1. You should consider the Hilbert space filling curve. It is actually its image. Hilbert's mapping, we didn't say any details there. The curve, which our closed line segment mapped onto that Hilbert iteration, at every step, the curve is uniformly continuous. So the mapping is uniformly continuous and its limit, therefore, is continuous. And every point in the unit square is an inverse image of the mapping, which means the curve covers every point of the unit square. That is why we call it space filling. And you need to really prove that it has the big dimension 0, 1, or 2. I'm going to tease this. So the properties of Lebesgue dimension is, it is topologically invariant. It is a topological invariant. So homomorphic spaces have equal Lebesgue dimension. And finite simplicial complexes. Here I need to really notice that currently all over the world, the topology was taught in a way that it is only point set topology. And the major examples which motivated topology was forgotten by every classroom at the moment in the world. I've been to US, in South Africa, everywhere. The topology was taught in a way that it is pathological. It is only pathological topology. But we have to really remember from history of mathematics that topology started with the earliest question is these two I'm talking about during these in these courses. And then the major examples are two types. One is called simplicial complex. You have a finite set of simplices and then try to put them nicely together and get a complex. And if it is one dimensional, then it's the graph. So you have zero-dimensional objects called vertices and one-dimensional objects called edges, and try to put them together so that the one-dimensional ones only intersect at zero-dimensional ones common boundaries. And you can generalize this to have higher dimension. Then in this case, the Lebesgue dimension is equal to the dimension of the largest dimension of the simplex with the largest dimension. The simplices are very easy to define, which are complete graphs actually. So K4 is the 3 simplex, K2 is the 1 simplex, K1 is the 0 simplex, and K5 is the 4 simplex. You can actually have that as a simplex in the 4-dimensional space. So there the dimension is clearly counted in combinatorial way. So you look at the complex and then you find, using a computer program, because it's finite, you find the simplex of the largest combinatorial dimension, and then its dimension is the Lebesgue dimension. You can easily prove, this is proved simply by proving the simplex, the dimension of the simplex to be equal to n. Normal space, then Lebesgue dimension is at most the upper inductive dimension. Monotonicity is true. And I included the proof, and I'm not going through it. The most important definition of a dimension of a topological space is Lebesgue dimension, and it is monotonous. Some people pronounce this word as monotonic, which I don't really want to use it because I always use monotonous, the French way of saying instead of German way of saying. And it can be proved easily. So it's 5 sentences or something. So I'm not going through it. So now, for metrizable spaces, the Lebesgue dimension is equal to. The metrizable spaces are normal spaces, as we mentioned 3 times already. And for normal spaces, this is an inequality. The left is at most the right. But for metrizable spaces, they are equal. So a student should now here at this moment, even before proving this, find a normal space which has strict inequality. And classes of normal spaces, of course, this is where the equality is true as well, infinitely many such spaces. These are normal spaces. And the Lebesgue dimension of Rn is n. For normal spaces, again, there is, oh yes. For normal spaces, this is repeat, because here we stated it already. I have actually done, I haven't stated it. Wait a minute. The monotonicity has an extra condition, closed subspace. We actually need a normal subspace of normal spaces for which the dimension is monotonous, if you are rigorous. Okay, I haven't seen this, but I have said it already. Now, consider a finite open covering of course, there is a finite open covering of this is compact, the closed unit disk in the Euclidean plane. And then this covering is defined such that no point in the disk belongs to more than 3 sets, because it has dimension 2, the Lebesgue dimension 2. So this is true. And remove all points in the disk that belong to 3 sets. Now you would start with any open covering, and then if some subset is some point is belonging to 3 sets, 3 open sets, then you just remove it from the space and then continue. Right? This leaves at least one, but maybe a finite number of holes in the disk, even in the unit square, if you start it with unit square. The remaining object is two-dimensional. Two-dimensional means that its Lebesgue dimension is still 2. At every finite step of repetition of this, you have a two-dimensional topological space. But what is in the, if you indefinitely carry out this operation by removing every point which is covered 3 times by any finite cover, open cover, at the end you have a space with dimension 1, because in the limit, there's no point which is covered by 3 open sets. Every point is covered by at most 2 open sets, which means its Lebesgue dimension is 1. Look at this. This is called Sierpinski gasket. Of course, Sierpinski gasket was done on unit square, and then it geometrically deletes things. But here we are topologically doing it by deleting points covered by 3 open sets for any given finite open cover. At any step of the process, the space has dimension 2. In the limit, the space has dimension 1. Because in the limit, there's no point is covered by at least 3 open sets from any open finite open cover. So you can have lower dimensional space as a limit of higher dimensional space. And this can be carried out for other dimensions like dimension at least 3. You have a 3-dimensional Sierpinski gasket, which is called Munger sponge. Munger sponge was done geometrically by first taking away the middle hole in all 3 directions. And then you have these remaining places, you have holes in 3 directions, take it away. This was a Munger sponge. But here we are not doing geometric thing. We are taking away points in n+1 open sets of any given finite open cover. So it doesn't look like the original Munger sponge. Munger sponge in any dimension, 3-dimensional case in 3 dimensions has dimension 1. You should prove this. It doesn't even have, we didn't even say it has dimension 2. Saying dimension 2 is easier because if you remove all the points covered by 4, at least 4 open sets away, then you might expect that the remaining points in the limit will be covered by at least 3 open sets, which means Lebesgue dimension is 2. But it is not. Its dimension is still 1. This is my first batch of slides. Any questions, you should really interrupt me. I'm very happy, as you can see, that I'm very enthusiastic about even this basic part of this course. There are even things we can do in this basic part. So I'd like to now stop sharing this slide and then open the second batch. Is that okay, everyone? Nobody is talking. Maybe some of you are sleeping. Oh no, this is not Professor Simanjuntak. I thought she was Professor. Okay. So now we have done with topological spaces and considered at least 3 different definitions of dimension of a topological space. Can you all see the screen? Raise your hands, please. Yes, thank you. So the second part is for what we call geometric space. What is a geometric space? Now, geometric means that it has classical geometric space means that it has a fixed curvature. Now we have differential structures on it. We don't need to worry about that too much because I'm definitely very ignorant about the differential geometry. but the geometric space is simply differential geometry object. I'm very ignorant about I think I have no error on this. I was spotting something. No, so now this is where, when we were in Lahore many times, Professor Thomascu and his students, in particular, now Professor Muhammad Imran, they started doing a lot of work about metric dimensions of graphs and infinite graphs, locally finite infinite graphs. But by the time I was attending their seminars, something like, this is probably about 15 years ago now, time passes so fast. I remember I have mentioned to Professor Thomascu that the proper place to study metric dimension is metric spaces. Only that the graphs happen to be very difficult finite metric spaces. And in this case, the finite ones are much more difficult than infinite ones. So by that time, I decided to turn my head away from finite or locally finite graphs, not completely, but sometimes, and go into metric spaces, for which this concept is the child at home. So we started that, and then my co-author, Professor Alan Bearden of Cambridge University, was visiting South Africa, and then he asked me what I was considering, and I said, not much. I'm not much of a researcher. I usually teach undergraduate. And then he said, well, you must be doing something because you are publishing. No, yes, I am publishing, but not much. So we discussed this question, and then we did something very nice together, very quickly. And after submission, 1 week, the paper appeared without change. So this is very good, because after that, the papers are like that. If you submit, then it comes out very quick in a good journal. So let X rho be a metric space with distance function rho. I don't use D for distance function because I use D for the diameter. And I don't want to mix up things to confuse students or readers. The rho was the original distance notation since Hilbert. And we use that. So now, if you have a subset, every set can be linearly ordered, of course, but this subset we are probably considering the most countably infinite. Therefore, the elements can be ordered. And then you look at every point in the space X, going the distance to that set. This is not the distance to the set, it's distance to the members of the elements of the set as a vector. If these distances are distinct for two different points, x, y, so if x is not equal to y, then the two distances are distinct. And this is the negative of converse, which English people call it contraposition in Latin. That doesn't mean negative of converse. And I hate that contraposition word because that confuses the students. This is negative of converse. If x is not equal to y, then these two vectors are distinct. So at least one component is not equal to each other. Then we call this subset to resolve the space, and then we take the smallest cardinality to be the metric dimension. This is for any metric spaces, and it was defined long before Harari and Melter paper in Blumenthal's distance geometry and its application book published in 1953. this definition was there. But graph theorists think that it was Harari and Melter, including Professor Johan Tomescu and his students, always quote only Harari Melter paper, which is not right. I stopped quoting that because this was defined in mathematics already a long time ago. And this can be regarded as a coordinate, and these coordinates have been used for finite graphs in glorious applications like GPS and so on. And they always cite these applications in their paper. I don't like that kind of mentality. So Blumenthal's paper was the original introduction of this concept for metric spaces, and Harari Melter paper was more than 20 years later. And many papers have been, I'm not going to even mention that or cite that. Many papers in finite graph theory have appeared with beginning introduction mentioning the glorious and politically correct applications. Now we turn to geometric space. There are three classical geometric spaces, and I don't want to worry about the differential geometry. I only need to know that they have constant curvature. So the classical geometric space is Euclidean, Riemannian, and hyperbolic. And in a paper we published together, we obtained these four results. I'm not going to go through in this paper, which was in a non-combinatorial journal. Now, these examples are not important, by the way. The important example, for example, finite graph, finite complete graph as a metric space, or infinite, then cardinality. You can have a countably infinite many vertices, and complete graph that is not locally finite. That is one example, and that you can actually have this also same statement is true for any cardinality. And for example, if the cardinality is greater than the innumerable infinity, at least an infinite cardinality, then the C minus 1 is equal to C, and there's nothing much about that. And this example, I don't like it, but this was the first example to show that there exists a subspace which has larger dimensions than the space, which means the monotonicity is certainly not true. But this is not a good example, as we will explain later. This is a one-dimensional example of a Cartesian plane, which has a metric dimension 3, but Cartesian plane has metric dimension any given finite number, but the metric dimension of the Euclidean plane, according to that definition, is 3. Because if you have a two-dimensional simplex, its vertices dissolve the whole set. Whatever small simplex doesn't matter. So what are classical geometry? Euclidean space, which is R to the n, linear algebra. That is it. Its curvature at every point is 0. Hyperbolic space, which is denoted by this outline h to the n-dimensional hyperbolic space, which is given by this Poincaré model 2. The path metric is given by differential element weighted divided by xn, where xn is positive. If xn was any arbitrary real number, then we were saying that the last coordinate is positive, so we're looking at the half space. And if it is not so, then you cannot put x as a denominator. Riemann space. Riemann space has constant dimension 1. Hyperbolic space has constant dimension -1. This is the sphere. This is a sphere. The length of the vector is 1 unit sphere in n+1 dimensional Euclidean space. This is n-dimensional sphere. And we prove that these three spaces have metric dimension exactly one more than the Lebesgue dimension. Now we're talking about Lebesgue dimension. It's not linear algebraic dimension at all. So that's why we have to have the topology spaces. And here we want to really have some glorious, politically good, I always want to use this phrase, politically good illustrations. Now we have a Western Hemisphere. Is this Western Hemisphere? Yes. Africa, for example, Johannesburg to Berlin. If you fly, if it is, the flight is taking the great circle arc, then it is the distance, shortest distance between 2 points. What is a great circle? If you have a sphere, then it has a center. A great circle passing through 2 distinct points on the surface of the sphere means that it is the sphere. There is a unique plane determined by the 3 points, the center and those 2 points we said distinct. This plane intersects the sphere in a circle. That circle is called great circle, and one of the 2 arcs, at least one of the 2 arcs, is called the distance. If the 2 points are antipodal, then there are 2 shortest paths in the space. Space is actually just 2-dimensional. The inside of the Earth is not used by the flight. You have to really understand, if you go straight line, then the flight will probably have to go through the Earth, and then it cannot manage. So this is what very rigorous definition by Euclidean axioms of a great circle and geodesic arc. Now, this is the bisector. Consider 2 points on the sphere, these 2 white points. The bisector is always a great circle. Then no student is asking, no colleague is asking, what happens if you define a bisector of just 1 point? Bisector of 1 point is the whole space, because every point in the space has exactly equal distance to that point from itself. Only one distance there, but there could be more arcs. Geodesic arcs, there could be more. So this is a bisector. In the Euclidean plane, the bisector, Euclid constructed with compass and ruler by any given 2 points in the Euclidean plane, and then put a radius which is greater than the distance between these 2, which can be measured by the compass. And then you draw circular arcs carefully on either side of the segment, and then they intersect in 2 points. Those 2 points uniquely determine a straight line, which is called the bisector by Euclid of the 2 points. And here the straight line is the great circle. This is the definition of a bisector. By the way, bisector is not a word that will encourage further research. It will kill it. I'm not going to talk about this in this talk. So lots of English words are used wrong, incorrectly in mathematics. For example, people only understand that number as pi. And not many English people know that it is the length of a circumference of a circle divided by a diameter length, and which should be called perimeter-diameter ratio. And it only happens that it is equal to that number pi for circle in the Euclidean plane. For other geometric objects, that number can be even integer or rational number. So there, when you call a name with the number pi, Greek letters, then you stop research. You stop research because nobody will progress there. So this was defined by Hilbert in any metric space. So this is a bisector. All this definition you can find in from Marcel Burger's Geometry, volume 2, page 332. If the 2 points are equal in any metric space, then the bisector, we didn't say that AB are not equal there in the definition, so this is allowed. The bisector is the whole space, definitely non-empty, if X is non-empty. If you are talking about only bisector being empty or non-empty, then here is one research result. And we made an observation that this observation was made by Professor Johan Tomescu and his students as well, although I didn't cite them here, that in any metric space, a subset resolves if and only if there exists no bisector containing it. Every one of them is, this is not a bisector, then doesn't resolve, then if and only if this is true. There must be a point so that it lies on the bisector. So this is the statement. Now in the Euclidean space, the bisector is just Euclidean bisector, which is done by the Euclid's compass and ruler. I did mention a paragraph saying that this word is not correct. This is a misnomer. If you understand what it is, it's a wrong name given to a child, and then this child suffers the name throughout his life. His mother gave him dog meat or something, or dog doesn't even eat in some Chinese or Zulu culture. Trash. The child's name is Trash because the first two child died. So now nobody will take him. So but then the child suffers all his life. Now we proved that the non-empty open subset of the Euclidean space has. This is known in this statement is known in Blumenthal's monograph. He mentioned n+1. I'm not going to prove. This is in Blumenthal's as an exercise. So, but because Rn itself is an open subset of Rn, then its dimension is n+. Now, in the hyperbolic space, if you take two vectors, we still call it them vectors, 2 points in a hyperbolic, n-dimensional hyperbolic space. Then, if they are not equal, then the bisector is equal to S intersect Hn, where S is an Euclidean sphere centered on the hyperplane plane n equal to x sub n equal to 0. Remember that in the hyperbolic Poincare model, that plane is not included in the space. But this sphere, the center is on that. So it's a semi-sphere. In two-dimensional hyperbolic plane with upper half plane model, you can see that the bisectors are semicircles with centers on the boundary, which is not included. In n-dimensional hyperbolic space, this is the proper Poincare model. In the 2-dimension, it is taking the open disk as the model of the hyperbolic plane. The further you go, the distances between 2 points, which are seemingly distances are equal to the 2 points in the distance of 2 points nearby to the origin, but their distances are much more. So that is this is the Poincare model in which the metric is. Because the length of this vector is more less than 1, this denominator is non-zero, actually positive. This is a non-negative number, therefore it's a metric, distance metric. And it is very easy to prove that metric dimension of Riemann space is n+1. And we're going to demonstrate this by the case n equal to 2 with graphics. Oh, no, not yet. Okay, we will not talk through this too much in detail. We also studied the dimension of, this metric dimension now, dimension of affine subspaces of the Euclidean space. Therefore, we use affinely independent. This is a very good exercise in linear algebra that if these vectors are linearly independent, then those vectors are affinely. And for any affine subspace, the same thing is true. The metric dimension relates nicely in these geometric spaces with the Lebesgue dimension. Let me check. So skip through the affine plane. And monotonicity is not true. This is the monotonicity definition. Now here, we have to be careful because Alan and I made a mistake. Of course, that example was nobody complained about. It's an example, no problem. And also, Professor Johan Tomescu and his students also claim similar examples. These are all wrong. If you really want to have monotonicity, the subspace must satisfy the condition of the ambient space as well as it has to be with its own intrinsic metric is the same as its ambient space metric. These two must have the same topological properties in order to talk about monotonicity of dimension. So this is why I was remarking when I saw the Lebesgue dimension, because it requires the subset to be closed. Of course, the whole space is also closed, that's fine, but you cannot really say that you should really have every normal space of a normal space is satisfied this monotonicity. You shouldn't say that this space is normal and then that we take an open subset or a subset, closed subset or subset with interior points and so on. Then you say that it's monotonous. Then you are not doing this question properly. In order to do this kind of question properly, the monotonicity is that the two spaces must satisfy the same topological conditions. That we have to remark, and then we did do it. So therefore, this example is no good. Then my PhD student Emil Lay and I did this later on, many years later, but we don't publish much, but this is a very good paper. We did prove that for metrics, there exists metric spaces. This is not unknown example, but he did work out this easily. So here we have a space of with 4 points. We use the perimeter of a circle. And X consists of the 3 points, X1, X2, X3. They are 2t distance away from each other, pairwise. And you put 3t. So it's so perimeter has for any positive number t, the perimeter is 9t. And then you put y at distance 1t away from x1 in the direction of x3. Doesn't matter which direction. Then the y resolve the space y, because let us verify this. Y has distance 0 to itself, x has distance 1, x1 has distance 1, x2 has distance 4, x3 has distance 2. So all distances are distinct. All points of the space distance to y are distinct, therefore y resolve. And now in the subspace, isometric subspace, the distances in the subspace are exactly the distances in the ambient space. The isometric subspace, because we are talking about metric space. Now we have it has to be isometric subspace in order to talk about monotonicity. This subspace cannot be resolved by any one point, because if you take, for example, x1, then x2 and x3 are both distance 3 away from x1. So you need to take 2 and then 2, 5. 2 is fine, because if you take x1, x2, then x1 has coordinates 0, 1, x2 has coordinates 1, 0, and 0, 3t, and 1, 3t, 0, and then x3 has coordinates 3t, 3t. So t is positive, therefore all 3 coordinates are distinct. So this is an example of isometric subspace or metric space whose the dimension is greater, strictly greater than the space. Now, time is up. we will probably stop here. But here we need, before we stop, I'd like to remark that this means that metric spaces are no good. So metrizable topological spaces are no good in order to have monotonicity. They can't work, which means non-topological spaces are definitely not good. So we need to have better spaces in order to talk about monotonicity.
Thank you so much, Professor Sheng Bau.